Disclaimer. Dear listeners, please be aware that this article is for information purpose only and may not in a whole holds the final facts or figures concerning this article concerning this subject matter. Everyone is strongly advised to carry out their own research into the subject before making a final decision about this article. We are not responsible for any loss or damage you may suffer as a result of this article. Please do not forget to like, share and subscribe to our channel. That will be greatly appreciated. In this article we are going to delve into the study of earthquakes and their unique characteristic and abilities. An earthquake is primarily caused by the movement of tectonic plates, which are large sections of the Earth's crust that float on the semi-fluid layer beneath them. These plates are constantly shifting, albeit very slowly, due to the convective currents in the underlying mantle. When the boundaries of these plates interact, they can become locked or stuck due to the friction between them. Over time, the stress and pressure at these locked boundaries build up until they exceed the strength of the rocks holding them in place. When the accumulated stress becomes too great, the rocks abruptly rupture, releasing a tremendous amount of stored energy. This sudden release of energy sends seismic waves radiating outwards from the source, which is known as the earthquake's epicenter. The seismic waves travel through the Earth's interior and cause the ground to shake, resulting in the shaking and displacement of objects and structures on the surface. Earthquakes are commonly characterized by their magnitude and intensity. Magnitude refers to the amount of energy released during an earthquake, which is measured using instruments called seismometers and represented by a numerical value on the Richter scale. The intensity of an earthquake, on the other hand, refers to the level of shaking and the damage caused in a specific area, which can vary depending on factors such as distance from the epicenter, local geology, and the depth of the earthquake. Earthquakes can trigger a series of secondary hazards, including landslides, tsunamis, and aftershocks. The severity of the impact of an earthquake depends on various factors such as the magnitude, depth, proximity to populated areas, and the preparedness of the affected communities. Scientists and engineers continually study and monitor earthquakes to better understand their causes, predict their occurrence, and develop measures to mitigate their effects. Overall, earthquakes are a natural consequence of the dynamic nature of our planet and the constant movement of tectonic plates. While they can be devastating, advancements in technology and knowledge have enabled us to improve earthquake preparedness, response, and mitigation strategies, ultimately reducing the risk and impact of these powerful geological events.
Earthquakes are measured using seismometers, which are sensitive instruments that detect and record the seismic waves generated by an earthquake. The data collected by seismometers provide valuable information about the intensity and magnitude of the earthquake. Magnitude is a numerical measure that represents the size or energy release of an earthquake. There are several different magnitude scales used, with the most widely known being the Richter scale. The Richter scale was developed by Charles F. Richter in the 1930s and is based on the amplitude of seismic waves recorded by seismometers. The Richter scale is logarithmic, meaning that each whole number increase on the scale represents a tenfold increase in the amplitude of the seismic waves and approximately 31.6 times more energy released. For example, an earthquake with a magnitude of 6.0 releases about 31.6 times more energy than an earthquake with a magnitude of 5.0. The Richter scale is open-ended, meaning there is no upper limit to the magnitude recorded.
Another commonly used magnitude scale is the moment magnitude scale, MW. The moment magnitude scale measures the total energy released by an earthquake, taking into account the area of the fault that slipped and the average amount of slip along the fault. The moment magnitude scale is more accurate for larger earthquakes and is the preferred scale for measuring earthquakes of magnitude 7.0 and above. In addition to magnitude, earthquakes can also be described in terms of intensity. Intensity is a measure of the effects and damage caused by an earthquake at specific locations. Various intensity scales, such as the Modified Mercalli Intensity (MMI) scale, are used to assess the level of shaking and the observed impact on people, buildings, and the environment. Intensity is determined through field observations, surveys, and reports from affected areas. It's important to note that while magnitude and intensity are related, they are distinct measurements. Magnitude represents the energy release of the earthquake at its source, while intensity reflects the effects of the earthquake as experienced at different locations. Overall, the combination of seismometer recordings and analysis of ground motion data allows scientists to determine the magnitude and intensity of earthquakes accurately. These measurements play a crucial role in understanding and assessing the potential impact of earthquakes, informing emergency response efforts, and contributing to seismic hazard assessments in earthquake-prone regions. There are three main types of seismic waves associated with earthquakes: primary waves, P waves, secondary waves, S waves, and surface waves. Each type of wave has distinct characteristics and travels through the Earth in different ways. Primary waves, P waves. P waves are the fastest seismic waves and are the first to be recorded by seismometers. They are also known as compressional waves because they cause particles of the medium, rock, soil, etc., to move back and forth in the same direction as the wave's propagation. P waves can travel through solids, liquids, and gases and are capable of passing through the Earth's inner core, outer core, mantle, and crust. They are characterized by a push-pull motion and can travel at speeds of up to 14 km per second in the Earth's crust. Secondary waves, S waves. S waves follow P waves and are slower than them. These waves are also known as shear waves because they cause particles of the medium to move perpendicular to the wave's propagation. Unlike P waves, S waves can only travel through solids and cannot propagate through liquids or gases. They are responsible for the shaking and side-to-side motion experienced during an earthquake. S waves travel at slower speeds than P waves, typically ranging from 3 to 8 km per second. Surface waves. Surface waves are the slowest of the three types of seismic waves and are responsible for the most significant damage during an earthquake. These waves travel along the Earth's surface rather than penetrating through it. Surface waves have two main types: love waves and Rayleigh waves. Love waves, L waves, cause horizontal shaking from side to side, similar to S waves. They are slower than S waves and travel just below the Earth's surface. Rayleigh waves, R waves, cause both vertical and horizontal rolling motion. They produce a rolling sensation and are responsible for the up and down movement of the ground. Surface waves, particularly Rayleigh waves, generally have larger amplitudes and longer periods compared to P waves and S waves. As a result, they can cause more extensive damage to buildings and structures. Understanding the behavior and characteristics of these seismic waves is crucial for seismologists and engineers in assessing earthquake hazards, designing resilient structures, and predicting the potential impact of earthquakes on communities. Scientists study and monitor earthquakes using a combination of seismology, geophysics, and various monitoring techniques. Here are some key methods and tools employed in the study and monitoring of earthquakes. Seismometers. Seismometers are instruments that detect and record ground motion caused by seismic waves. They are strategically placed in networks across the globe to monitor seismic activity. Seismometers measure the velocity, amplitude, and frequency of seismic waves, providing valuable data for earthquake analysis. Seismic networks. A network of seismometers is established to detect and record earthquakes. These networks enable scientists to locate the epicenter, determine the magnitude, and analyze the characteristics of seismic events. Data from seismometer stations are collected and analyzed to create seismic waveforms and earthquake catalogs. Seismic monitoring stations. Permanent and temporary seismic monitoring stations are set up in seismically active regions to continuously monitor ground motion. These stations transmit real-time data to seismic centers for analysis, allowing for rapid earthquake detection and response. Global seismic networks. Collaborative efforts among countries have established global seismic networks that share data internationally. This cooperation allows for a comprehensive understanding of global seismic activity and enhances earthquake monitoring and early warning systems. Seismic arrays. Seismic arrays consist of multiple seismometers placed closely together to capture and analyze seismic waves more accurately. By combining data from multiple sensors, scientists can obtain a more detailed understanding of an earthquake's source and characteristics. GPS and INSAR. Global Positioning System (GPS) and Interferometric Synthetic Aperture Radar (INSAR) technologies are used to monitor ground deformation associated with tectonic plate movements. By measuring small changes in land surface position, scientists can detect and study slow, gradual movements and strain accumulation along faults. Geodetic surveys. Geodetic surveys involve precise measurements of ground movements using techniques such as leveling, GPS, and satellite-based radar. These surveys provide valuable data on crustal deformation, strain accumulation, and the potential for future earthquakes. Geophysical imaging. Various imaging techniques, such as reflection and refraction seismology, are used to study the Earth's subsurface structures. By analyzing seismic wave behavior and imaging the subsurface, scientists can gain insights into fault structures, crustal features, and potential earthquake sources. Earthquake catalogs and databases. Earthquake catalogs compile data from multiple sources to create comprehensive databases of earthquake events. These catalogs include information such as location, time, magnitude, and focal mechanisms. By analyzing these catalogs, scientists can identify patterns, trends, and seismicity rates in specific regions. Earthquake early warning systems. Advanced seismic monitoring systems can detect the initial, less damaging P waves of an earthquake and provide warnings to regions located farther from the epicenter. These systems help mitigate the impact of earthquakes by allowing for timely alerts and actions to protect lives and infrastructure. By utilizing these methods and technologies, scientists can continuously monitor and analyze seismic activity, understand earthquake processes, improve hazard assessments, and develop strategies for earthquake preparedness and response. Earthquake prediction. The ability to forecast the occurrence, timing, and location of future earthquakes with a high level of certainty remains a challenging and complex task. While scientists have made significant progress in understanding earthquakes, accurate short-term earthquake prediction is still elusive. However, several techniques and approaches are employed in earthquake prediction research. Here are some of the main techniques used. Seismic monitoring. Seismometers are deployed in earthquake-prone regions to continuously monitor and record seismic activity. Analyzing patterns and trends in seismicity can provide insights into the likelihood of future earthquakes. Unusual seismic activity, such as an increase in the frequency or intensity of earthquakes in a specific area, may indicate an increased likelihood of a larger earthquake occurring. Foreshock analysis. Foreshocks are smaller earthquakes that occur before a larger mainshock. Studying the characteristics and temporal patterns of foreshocks can provide valuable information about the potential for a larger earthquake. However, accurately identifying foreshocks and distinguishing them from regular seismic activity is a challenging task. Changes in groundwater and well levels. Some studies suggest that changes in groundwater levels and well behavior may precede an earthquake. Monitoring water levels, changes in well pressure, and geochemical variations in groundwater chemistry are techniques that are being explored for earthquake prediction. However, these methods are still under investigation and require further research to establish their reliability. Geodetic measurements. Geodetic techniques, such as GPS and satellite-based radar, INSAR, are used to monitor crustal deformation and strain accumulation along fault lines. These measurements can provide information about the buildup of stress and the potential for future earthquakes. However, geodetic measurements are more effective in long-term forecasting rather than short-term prediction. Animal behavior. Some studies have suggested that animals may exhibit unusual behavior before an earthquake. Observations of changes in animal behavior, such as the migration or movement of certain species, have been investigated as potential precursors to seismic events. However, the relationship between animal behavior and earthquakes is still not well understood, and more research is needed to establish reliable correlations. It's important to note that despite extensive research, no method has yet demonstrated consistent and reliable short-term earthquake prediction. Earthquakes are complex events influenced by a variety of factors, and their occurrence remains largely unpredictable on short timescales. The focus of current efforts is shifting toward earthquake early warning systems, which aim to rapidly detect earthquakes and provide warnings to affected areas, allowing for prompt response and mitigation measures. Earthquakes play a significant role in the formation of mountains and other geological features through the process of tectonic activity. Tectonic activity refers to the movement and interaction of Earth's tectonic plates, which are large, rigid pieces of the Earth's lithosphere. Here's how earthquakes contribute to the formation of mountains and other geological features. Plate tectonics. Earthquakes are primarily a result of plate tectonics, where the Earth's lithosphere is divided into several large plates that float and interact with each other. The boundaries between these plates are areas of intense seismic activity. The three main types of plate boundaries are divergent, convergent, and transform boundaries. Convergent boundaries. At convergent plate boundaries, two plates collide or come together. When this happens, one plate is typically forced beneath the other in a process known as subduction. The collision and subduction of plates generate intense pressure and stress, leading to earthquakes. These earthquakes can be shallow or deep and are often associated with the formation of mountains, such as the Himalayas, Andes, and the Alps. Transform boundaries. Transform plate boundaries occur where two plates slide horizontally past each other. The friction between the plates can cause them to become locked, resulting in a buildup of stress. When the stress exceeds the strength of the rocks, it is suddenly released, causing earthquakes along the transform fault. The San Andreas Fault in California is a well-known example of a transform boundary that has generated numerous earthquakes. Rift zones and divergent boundaries. Earthquakes also occur along rift zones and divergent plate boundaries where the Earth's lithosphere is being pulled apart, leading to the creation of new crust. As the lithosphere stretches and fractures, earthquakes happen along the rift zone. Over time, these repeated seismic events can contribute to the formation of rift valleys, such as the East African Rift Valley. Faulting and uplift. Earthquakes can cause faulting, which is the breaking and displacement of rocks along a fault line. Large earthquakes along faults can lead to vertical or horizontal displacement, resulting in the uplifting or lowering of the Earth's crust. This uplift can contribute to the formation of mountains, plateaus, and other topographic features. It's important to note that while earthquakes contribute to the geological processes that shape the Earth's surface, they are just one component of a larger dynamic system involving tectonic forces, erosion, weathering, and other geological processes. The cumulative effects of seismic activity over millions of years shape the Earth's landscape and contribute to the creation and evolution of mountains and other geological features. Throughout history, there have been numerous significant and devastating earthquakes that have had profound impacts on human lives and infrastructure. Here are some of the most notable examples. 1556 Shaanxi earthquake, China. This earthquake, often referred to as the deadliest in recorded history, struck Shaanxi Province, China, on January 23, 1556. With an estimated magnitude of 8.0, it caused extensive damage and loss of life, resulting in an estimated death toll of approximately 830,000 people. 1755 Lisbon earthquake, Portugal, on November 1, 1755. A massive earthquake struck Lisbon, Portugal, with an estimated magnitude of 8.5 to 9.0. The earthquake was followed by a tsunami and widespread fires, leading to the destruction of much of Lisbon and resulting in the deaths of tens of thousands of people. 1906 San Francisco earthquake, United States. This earthquake occurred on April 18, 1906, in San Francisco, California. With an estimated magnitude of 7.9, it caused widespread destruction and triggered massive fires that ravaged the city for several days. The earthquake resulted in an estimated death toll of around 3,000 people and caused significant economic losses. 1964 Great Alaska Earthquake, United States. On March 27, 1964, the Great Alaska Earthquake struck the Prince William Sound region of Alaska. With a magnitude of 9.2, it remains the most powerful earthquake ever recorded in North America. The earthquake and subsequent tsunamis caused widespread damage and loss of life, with over 130 fatalities reported. 1976 Tangshan Earthquake, China. The Tangshan earthquake struck the city of Tangshan in northeastern China on July 28, 1976. With an estimated magnitude of 7.6, it caused catastrophic damage, resulting in the deaths of approximately 242,000 to 655,000 people, making it one of the deadliest earthquakes in history. 2004 Indian Ocean earthquake and tsunami. On December 26, 2004, a massive undersea earthquake with a magnitude of 9.1 to 9.3 occurred off the coast of Sumatra, Indonesia. The earthquake triggered a devastating tsunami that affected numerous countries bordering the Indian Ocean. The death toll exceeded 230,000 people, making it one of the deadliest natural disasters in recorded history. 2010 Haiti earthquake. On January 12, 2010, a destructive earthquake struck Haiti, primarily affecting the capital city of Port-au-Prince. With a magnitude of 7.0, the earthquake caused significant damage, including the collapse of numerous buildings and infrastructure. The death toll is estimated to be between 230,000 and 316,000 people. These are just a few examples of significant and devastating earthquakes from history. Each of these events had profound humanitarian, social, and economic consequences, highlighting the importance of earthquake preparedness, response, and mitigation measures. During an earthquake, taking appropriate safety measures can significantly increase your chances of staying safe. Here are some essential safety measures individuals can take. Drop, cover, and hold on. When you feel the shaking, immediately drop to the ground to prevent being knocked over. Take cover under a sturdy piece of furniture, such as a table or desk, and hold on to it until the shaking stops. This helps protect you from falling objects and provides some protection from collapsing structures. Stay indoors. If you are inside a building, stay there during the shaking. Moving around during an earthquake can be dangerous due to the risk of falling objects and structural damage. Avoid doorways as they are not necessarily safer than other parts of a building. Instead, seek shelter under sturdy furniture. Stay away from windows. Move away from windows, glass, mirrors, and other items that could shatter during the shaking. Glass fragments can cause severe injuries. Avoid elevators. Use the stairs instead of elevators during an earthquake. Power outages or equipment malfunctions can leave you trapped inside an elevator. Secure heavy objects. Secure heavy furniture, appliances, and other objects that could potentially topple or fall during an earthquake. This includes bookshelves, cabinets, TVs, and water heaters. Use straps, brackets, or other appropriate fastening devices to secure them. Stay clear of exterior walls. Avoid standing near or against exterior walls, as they can collapse or have objects fall off them during an earthquake. Stay calm. It is essential to remain calm during an earthquake. Panic can impair your judgment and hinder your ability to take appropriate safety measures. Have an emergency kit. Prepare an emergency kit that includes essential supplies such as water, non-perishable food, a first aid kit, flashlight, batteries, and a portable radio. Keep the kit in an easily accessible location. Develop an emergency plan. Create a family emergency plan that outlines how to communicate, where to meet, and what to do in the event of an earthquake. Practice this plan regularly with all family members. Be informed. Stay informed about earthquake risks and preparedness measures in your area. Follow official guidance and instructions from local authorities and emergency management agencies. Remember, earthquake safety measures can vary depending on the specific circumstances and location. It is recommended to consult local authorities or emergency management agencies for region-specific guidelines and recommendations. Earthquakes can have significant impacts on the environment and ecosystems. The effects can vary depending on the magnitude of the earthquake, the proximity to populated areas, and the specific geological and ecological characteristics of the affected region. Here are some ways earthquakes impact the environment and ecosystems. Surface rupture and ground deformation. Powerful earthquakes can cause the ground to rupture and deform, resulting in visible changes to the landscape. Large displacements along faults can alter the natural topography, create new landforms, and disrupt ecosystems. This can affect drainage patterns, water flow, and vegetation distribution. Landslides. Earthquakes can trigger landslides, particularly in hilly or mountainous areas. Shaking can destabilize slopes, leading to mass movements of soil, rock, and debris. Landslides can bury vegetation, alter river courses, block roads, and pose risks to human settlements and ecosystems. Tsunamis. Underwater earthquakes can generate tsunamis, which are large ocean waves that can travel across long distances. When these waves reach the coast, they can cause significant flooding, erosion, and destruction of coastal habitats. Tsunamis can also introduce saltwater into freshwater ecosystems, impacting aquatic species. Ground shaking and liquefaction. Strong ground shaking during earthquakes can cause damage to infrastructure and disrupt ecosystems. It can uproot trees, collapse buildings, and damage habitats. In areas with loose, water-saturated soil, shaking can induce liquefaction, where the soil temporarily loses its strength and behaves like a liquid. Liquefaction can result in the sinking, tilting, or destabilization of structures and can affect underground water resources. Changes in water sources. Earthquakes can impact underground water sources, such as aquifers and wells. Ground shaking can alter the flow of groundwater, leading to changes in water availability and quality. This can have implications for both natural ecosystems and human water supplies. Habitat alteration. Earthquakes can cause habitat alteration and fragmentation, disrupting ecosystems and species distribution. Landslides, ground deformation, and changes in water sources can impact the suitability of habitats for various plant and animal species. Some species may struggle to adapt to these changes, leading to shifts in ecological communities. Disruption of ecological processes. Earthquakes can disrupt ecological processes and relationships within ecosystems. Disturbances such as landslides, changes in water flow, and habitat destruction can affect the availability of resources, disrupt food chains, and impact species interactions. Long-term ecological succession. In the aftermath of earthquakes, ecosystems undergo a process of succession, where new plant and animal communities gradually establish and replace those that were disrupted or destroyed. This process can take years or even decades, and the composition and structure of the ecosystems may change as a result. It's important to note that ecosystems are resilient and have the capacity to recover from earthquake impacts over time. However, the severity of the impact and the resilience of the ecosystem depend on various factors, including the frequency and magnitude of earthquakes, the degree of human intervention, and the ability of species to adapt to changing conditions. In conclusion, earthquakes are powerful natural phenomena that have profound effects on human lives, infrastructure, and the environment. These seismic events, resulting from tectonic activity, can occur along plate boundaries and within the Earth's crust, leading to ground shaking, surface ruptures, and ground deformation. The impacts of earthquakes are wide-ranging and can be devastating, causing loss of life, property damage, and significant changes to the natural world. From a human perspective, understanding earthquake safety measures is crucial for minimizing the risks and mitigating the potential consequences. Dropping, covering, and holding on during an earthquake, staying indoors, and avoiding hazards like falling objects and shattered glass can significantly increase personal safety. Additionally, preparedness through emergency kits, family plans, and staying informed about earthquake risks are essential components of earthquake resilience. On an environmental level, earthquakes shape the landscape and impact ecosystems. Surface ruptures, landslides, tsunamis, and ground shaking can alter habitats, disrupt ecological processes, and lead to changes in species distribution and interactions. However, ecosystems possess remarkable resilience, and through ecological succession, they can gradually recover and adapt to the new post-earthquake conditions. While scientists continue to study earthquakes and improve their understanding of these complex phenomena, short-term earthquake prediction remains a challenge. Instead, the focus has shifted towards early warning systems that aim to rapidly detect earthquakes and provide advance alerts, enabling individuals and communities to take timely actions to protect themselves. Earthquakes serve as a reminder of the dynamic nature of our planet and the interconnectedness between geological processes, human societies, and the natural world. By recognizing the risks, implementing safety measures, and fostering a culture of preparedness, we can enhance our resilience and better cope with the impacts of earthquakes, promoting the safety and well-being of individuals, communities, and ecosystems in seismic-prone regions. Thanks for watching.